Now that we've talked about synchronization, we can focus on the other piece that's provided by a monitor object, which we call coordination. So in this set of slides, we're going to talk about how built-in monitor objects provide these wait and notification, wait notify or waiting and notification mechanisms that are used to coordinate threads that run in a concurrent program. And to illustrate this stuff, we'll be looking at this implementation, the simple blocking bound queue, and we'll look at this from a couple of different perspectives. But first, let's talk about built-in waiting and notification. So as we saw before, the synchronized methods only got you so far, right? They avoided race conditions, but you'd end up spinning, and therefore your solution had deficiencies, particularly performance deficiencies. Built-in monitor objects to counter this provide you a few extra things, and they allow threads to coordinate their interactions. And they do this via the wait, notify, and notify all methods. As you'll see, wait is used to cause the current thread to wait until another thread invokes the notify or notify all method for this object. And remember, when you call wait, it'll automatically release the synchronized lock, the intrinsic lock. Notify is used to wake up one thread that's waiting on this object's monitor, and notify all wakes up all the threads that are waiting on this object's monitor. And that, of course, can lead to the thundering herd problem. So use notify all carefully, although you may have to use it when you're programming with built-in monitor objects for reasons we'll talk about shortly, because of the deficiencies that they have. Here's a picture that illustrates kind of the visualization of a monitor object. If you go to the monitor Wikipedia link and you read about implicit condition variable monitors, that's the way that Java works. It has this thing called an implicit condition variable monitor. And the way it works, as we'll see here, is you have an entrance queue, which is basically the intrinsic lock. That's what's used to serialize access to the monitor. And then you have a wait queue. And the wait queue is where you let threads park themselves waiting for the condition or conditions to become suitable to make forward progress. And of course, the entrance queue is used to guard access to the critical section, so that's how you get into this thing, by waiting in the wait queue. And when you reach a point where you can't make forward progress, you then wait, and that parks you over here on the wait queue and allows someone else to go into the critical section. All the notify and notify all calls apply to the wait queue. That's what they're working on, and moving things in and out of the wait queue. Okay, so here's a little snippet of simple blocking bounded queue, which you can look at. We'll look at this in more detail later, but this is just a quick view. And this illustrates kind of how the various pieces work. So as you might imagine, when the queue is full and you call put, that's going to cause the thread to wait. And this, of course, is the guarded suspension pattern, right? So when put is called, we call synchronize, so we get ourselves in the critical section. And while the queue is full, we're going to wait. Remember, when we call wait, that's going to automatically release the synchronized lock and go to sleep. Now, the interesting thing here is, let's assume for sake of argument the queue is not full, so we go ahead and add something to the queue. We're then going to have to call the notify all method. And that's going to wake up all the threads on the wait queue, irrespective of whether they're trying to put something in the queue or take something out of the queue. And the reason for that is that waiters in this implementation, which is a very simple implementation, are non-uniform. And you'll see why when you look at the code a little bit more carefully as we talk about that. And the reason we have to call notify all here is due to the limitations of Java built-in monitor objects, where there's only one wait queue. This is the implicit condition variable monitor that I was just talking about. Okay. Okay, non-uniform. It means that we're going to have two different conditions sharing the same monitor condition. So we're going to have to check if the queue is empty or the queue is full. As we'll see later, or you think back to our discussion we had a couple weeks ago about the use of condition object. If you remember with condition object, we had a not full condition and a not empty condition. We had two separate conditions, two separate wait sets. So then any thread that was waiting on that condition was a uniform waiter. Whereas here they're non-uniform because there's actually two conditions that could be waited on the same condition, which is, again, part of the limitations of monitor objects. When you call take, that's called and if the queue is empty, you have to wait. So that'll wait, because that's a different condition. We're using the same condition to wait on a different condition expression. And when we finally get something out of the queue, we're going to notify everybody, and then we're going to return the item. Again, we have to notify everyone because of the non-uniformity of these things and because of the wacky quirks of the Java condition object limitation for monitor object. We'll talk more about this when we get into the implementation, because this may look a little curious at first glance, but I'll explain that. So we're going to talk more about put and take here in just a second. I just want to give you this notion of how monitor objects work in a common case. Built-in monitor object synchronizers are typically implemented by POSIX mechanisms. Obviously, if you're running on a Unix platform, if you're running on Windows, they have a different implementation. But if you're running on Linux or Android, they're going to use the so-called POSIX mechanisms. So the entrance queue is typically implemented by a POSIX recursive mutex. Read more about that here. And wait queues are typically implemented by a single POSIX condition variable per monitor object. You can read more about condition variables here. And condition variables just allow you to have a queue of threads waiting to get their chance to go and run. They're very similar to Java condition objects, but they're typically written entirely in C as opposed to Java. Okay, so that's the end of the first part of this lesson, talking about coordination. Okay, so let's now talk about the second part of the lesson on coordination of Java monitor objects. And what I'm going to do here is I'm going to show you how to visualize how a built-in monitor object can be used with the wait notify mechanisms we've been talking about. We'll show a visualization of it first, and then in the next part of the lesson, we'll show the code. So once again, you can download the code here. This is kind of an overall picture of what we're going to be looking at, illustrating the various parts involved, and that's kind of the canonical monitor object diagram where we have sort of the entrance queue area, the critical section, and the wait queue area. And we'll be zooming in, kind of looking at that. But by the way, I spent a lot of time on that animation. Very cool. So we're going to have a queue of threads that'll be blocked on the entrance queue, and those are waiting to get into the critical section. And then we can have a queue of threads waiting on the wait queue, waiting to have the condition either be not empty or not full, depending on what you're waiting for, whether you're putting or getting. And the key thing to remember, again, is this illustrates the use of an implicit condition object. There's only one of these things per monitor object, which makes it more complicated. So over here, kind of on the right-hand side, I'm just showing you sort of what the code looks like at a high level of the test program. This is just notional. The actual test program is more complicated than this, but this gives you a basic idea. So we're going to have a thread here. This is the consumer thread, and as you can see, it's going to be basically sitting here while we're not done. We're going to go ahead and take something out of the queue, and what that'll do is when take is called, it'll go ahead and enter the monitor object through its entrance queue. Let's assume for sake of argument that there's nothing there. So we come in, we acquire the lock with thread T1, and we get inside the critical section. And now, while the list is empty, we're going to have to wait. And let's assume for sake of argument the queue was empty, so that the thing is going to have to wait. What's going to happen at that point is we're going to go ahead and move. As you can see, we move from the critical section where we're running inside the monitor object. We move out here to the wait queue, and that's going to put us to sleep. So thread T1 will be asleep on the wait queue, and of course that'll also release the monitor lock so someone else can come along and put something in the queue. If the monitor lock wasn't released, then we'd have deadlock, which is why if you take a look at your programming solution for the fair queue, you have to be very careful that you release the intrinsic lock or you'll end up with deadlock, which is not a good thing. All right, so with this guy parked over here and suspended, thread T2 comes along. And in this case, it's going to go ahead and put something into the queue. So we're going to enter the monitor object. We're going to acquire the lock because it was released by thread T1. So far, so good. And now, if the queue is full, we're going to wait. Well, obviously, if somebody's blocked waiting for the queue to be not empty, then it's not going to be full unless we have a queue with nothing in it, which would be bad. So in this particular case, we're not going to have to wait. We're going to add the message to the list, and then we're going to go ahead and notify everybody to wake up. Now, in this particular case, there's just one thread that's blocked in the wait queue, but in a more complicated test program with lots of threads that are producing and consuming on the same queue, there could be lots of threads. So when we call notify all those threads are going to wake up, whether they're producers or consumers, and they're all going to come tromping down to try to get access to the critical section through the intrinsic lock, which of course is the thundering herd problem. So we release the lock, we exit the monitor. This guy then, the other thread's going to wake up because it's been notified, or everybody's been notified, but there just happens to be one in this case. That's going to unblock in the monitor condition. It's going to be able to come in and acquire the lock because nobody else is holding it. And now at this point, the queue is no longer going to be empty, so it doesn't have to wait this time. So it'll go ahead and notify everybody to wake up, and then it's going to go ahead and remove an item from the queue. Now this is a little curious. So you might think to yourself, why are we notifying everybody and then removing the item from the queue, as opposed to removing the item from the queue and then notifying everybody? And the reason we can do this is because the monitor lock is still held. So even though we've notified everybody, they can't get into the critical section until we release the lock. So there's really no problem doing this, and it just made the code ever so small, so ever so much shorter. If I was really nervous about this, which it doesn't really matter in practice, I could have first gotten the item off the list, stored it in the local variable, then called notify all, and returned the local variable. But it doesn't matter because nobody's going to be able to update the list, linked list implementation, until the monitor lock is released. So then we go ahead and return, the lock is released, we leave the monitor of it. Okay, so that's kind of a visualized view of how everything works. We'll look at the code in a second, but I just wanted you to get the high-level perspective on what's going on. And it's often very useful, by the way, when you're doing your code for the assignment, you might want to draw a picture like this and think through the steps that are happening, what's being released, what's being acquired, and so on, because it'll help you to visualize what's going on concurrently. Okay, so this is the third and final part of this lesson on coordination, and now we're just going to look at the implementation in Java so you can see in more detail how it would work under the hood. So we'll do a code analysis of our simple blocking bounded queue example, which you can get here, this link. And as you can see, there's some internal state. We have a list, basically a linked list, and a capacity. And that's the state that has to be protected against race conditions. And you can see here we're going to implement this with an array list, and we're going to give it a certain capacity. You don't need to protect the constructor against race conditions, and that, of course, is because the constructor is only going to be called in a single thread. If a constructor is called in multiple threads, man oh man are there problems, because that means that your constructor is being called in multiple threads of the same object, which would be bad. So you don't have to worry about that. Now, having said that, in this particular case, you'll notice that all we're doing here is we're allocating stuff that's part of these elements here. But the main thing to note is that if there was some shared state that was shared by other threads, then we might have to use synchronized statements inside the constructor if it's accessing some global variable, for example. So just because it's in the constructor doesn't mean it's always sequentialized. It depends on what the constructor is accessing. Now here's another super duper subtle question. Remember we've been talking about visibility related issues, about when something is actually visible to other threads. And so one thing that's not really that clear in the Java spec is if you allocate these fields in a constructor and then you spawn other threads, how do those threads know that they get access to this stuff? And that's a bit underspecified in Java, how that all works. But we'll take it at the moment for granted that constructors are going to properly get their values pushed out to other threads that may need to start running, and we'll have visibility to the fields that are allocated here. Okay, so now let's take a little bit more detailed look at take and put. So each call to take, let's say in T1, will acquire the intrinsic lock, and then it'll have to wait while the queue is empty. Make sure that you always have wait in a loop, because otherwise you'll have surprises. And the reason that you have to do this is that if this particular thread is reawakened, it might not be the case that the queue is not empty. So you always have to make sure you check. And the reason why this is the case is the reason why we can't be sure of this is because there's only a single wait queue, but there's multiple things that are happening. We're adding stuff to the queue, we're removing stuff from the queue. There's multiple non-uniform waiters in this example, so we need to make sure we check things in a loop. You can't assume that the expression is always true because of concurrency non-determinism. And then you also have to watch out for these so-called spurious wake-ups, which I told you are like unicorns. They occur very infrequently, but if you're super duper paranoid, you probably want to check for that case. You can find out more about spurious wake-ups here. The thread that's blocked on wait won't continue until it's notified that the condition expression may be true. And so how does that happen? Well, here was take, here's put. So if we're another thread, thread T2 calls put, when it wants to put something on the queue, it of course has to acquire the lock. And then assuming the queue isn't full, it'll go ahead and add something to the queue, and then it's going to go ahead and won't be full, and then it's going to call notify all. And once again, we're using notify all here because the fact there's only a single wait queue, so we have to notify everybody, even though that's massive overkill in this case. And that would, of course, then, when notify all is called, that'll cause take to wake up, and wait will return, and it'll go ahead and obtain the lock, reevaluate the condition expression. Let's assume for sake of argument it's no longer empty. It'll then notify everybody that wake up, and it'll go ahead and return the item from the front of the queue. And once again, it's okay to call notify all first because we aren't going to release the lock until this little curly brace thing is in, until the scope is done. Okay, any questions about that? Just a more detailed breakdown. So that's basically the end of that implementation. What I want to do now is I want to go ahead and run the program. So here is the code. Here's the program. Hopefully it'll work. Okay. All right, you can see number one. I don't know if you remember how long it took to run that other piece of code, but it sat there and chugged away for a while, right? And this took, basically 7 milliseconds, whereas the other one took seconds to run. It was way slower. And if we increase the size, you can see it still zip through that really quickly. So let's go take a look at the actual implementation of this stuff, and that may help so you can see what it's doing and why it's better. And I'll also run the regression test here in a second as well. But first, let's go ahead and take a look. Let's go take a look at the...
What was the difference between the two again?
The first one that we had looked at was the one that used synchronized statements alone and didn't use wait and notify. So it spun. Remember how we took a look at the count of the nulls, and there was a lot, for 100,000 NQs and DQs, there was like 27,000 times when it came there and there was nothing in it, right? Well, this implementation doesn't have that problem because it uses the synchronized statements in order to do its thing. Let's see, let's go ahead and clear these guys out. Make sure we get everything back to 0. Okay. All right, so let's take a look at the Android implementation. Here is the unit test. Hopefully that'll work. Oh, of course it doesn't work. Unreachable statement. Why? Oh. All right, that looks better. All right, so you can see that it ran really fast. And when we look at the code, we'll figure out why. So here's this is the test program. This is SimpleBlockingBoundedQueue, and then let's go look at the SimpleBlockingBoundedQueue test. So this is similar to what we had before. There's just a couple really important differences. One of the things, as you can see here, is before we'd called
before the producer, that's this guy here, the producer thread had used offer. And if you recall, what offer does is offer tries to put something in the queue, but if the queue is full, it returns false and doesn't actually do anything. But it was synchronized, so at least it wasn't going to have race conditions. In this particular case, because we're using put and we've implemented put correctly, when we call put and the queue is full, this thread will block. So first of all, it'll never have a situation where it's going to spin because it's going to wait until there's something, until the queue is not full. So that code up there is a little bit simpler, and it'll always do the right thing. When we come down here and look at the consumer, what the consumer does, consumer thread, it's going to run, and in this case, it's going to call take as opposed to poll. Remember, poll, we had to sit there and loop on poll, calling poll until we got a non-null result because the queue could be empty to start out with. If take finds an empty queue, it just blocks and puts itself to sleep. So we're always guaranteed to get an item back from this. And then here we're going to iterate through the whole thing, and once again, the code is much simpler because we don't have to worry about blocking, or we don't have to worry about not getting an item back because it's going to block when we call take. So we'll always get an integer back, and then it just checks to make sure that they're properly ordered, the queue is working correctly. So this code here is never going to spin. It's going to wait, which is, as you can see, a lot faster. Yes? You would hope that they're not on the waiting queue at the same time. I think the condition under which the producer and consumer thread were on the waiting queue at the same time is if you made a queue that had nothing in it, it had a size of 0. So that would be the only case where they would have that.
So it is not the in the waiting queue at the same time, so why we are using multiple? We can only use one.
No, because when you call here, all right. So this is a great question. So the question is, I'm trying to think of what I can use as a prop to illustrate this. If you only have one thread that's producing and consuming, this is not an issue. But if we have multiple threads, it's an issue. So let's see. Maybe you can see here. So this is the queue. I'll draw it like that. And let's assume, for sake of argument, I've got a bunch of producer threads, right? So we've got a bunch of threads up here, a bunch of them. And then down here, I have a bunch of consumer threads. And let's assume, for sake of argument, that I'm going to use notify instead of notify all. So all of these guys, let's do this case where we're blocking. All of these threads are blocked because the queue is empty at this point. So you've got 4 threads that are empty. And this guy comes along and is going to put something into the queue. But let's say, for sake of argument, that just at the time that happens, another thread comes along, right? So what can happen in this case is if we just call put, it's not clear who's going to be awakened. So it might be one of these guys, or it might be somebody else. So you have to be very careful with those things so you don't end up in a situation where you've got the notify being taken by somebody who really can't do anything with it. So that's the situation where you have to be really careful. Okay, so the rest of the test is basically the same. The main point I wanted to get across with this example was that the version that's synchronized is alone with no notify and wait mechanisms. That one is going to be a lot more inefficient, even though it's correct, because it has to spin, or because the test program has to spin. Whereas this implementation doesn't spin, and so as a result, you don't have to worry about that. It'll block.